Me too. And because I have a herniated disc in my back, so this solution is really important to me, to seeing my back better through an X-ray, actually through an MRI, really. How about a CAT scan? I actually have not had a CAT scan. And who's run a regression in their lives? Okay, so this is relevant to everybody. What I'm talking about today is about inverse problems. So an inverse problem is anytime you want to compute information about some interior property using exterior measurements. So that's what a regression is, right? You have a X matrix, usually, y equals beta times x plus some error term, and eventually to solve for beta, you're going to need to invert that x. So x tells you something is exterior measurement, and beta is going to be your interior explanation. And so we have inverse problems all the time in X-rays. So if you have a image, you're going to shoot rays at it. You don't know the image, but you're going to shoot rays at it, and you're going to collect information on the other side. And so it's a similar sort of problem. Okay, so the problem is, I just already said this, but X is my back, and you can tell, if you have a herniated disc, you can tell because the space between the discs are smaller, and also, this is non sequitur, the sides of your disc start to curve because there's less and less cushion between them. So you want to be able to see these things well. So we don't know X, but we can throw A at X. So A is going to be rays shot at my back, and each ray is a vector. And we're going to collect B on the other side. Okay, so then the problem, all we have is just an inverse problem. It's AX equals B. We want to solve for X. Remember, X is my back, it's the image. So X equals A inverse B. So we need to invert A. Okay, A at my back, B on the other side, X is the image. We want to solve for X. So most inverse problems that are large scale have ill-conditioned linear systems. So you have a matrix X, and the vectors tend to be collinear, and so the matrix itself is hard to invert or singular. So what a lot of packages will do is use a pseudo-inverse method to invert the matrix. So if you've ever done a regression where you know there's some collinearity between your vectors or between your variables, and the package will find a solution for you, but maybe between variable 1 and 2, there's a lot of collinearity, and you'll see that the coefficients on those variables are going to be widely separate. Like one will be like plus 1,000, the other one will be like minus 1,000. So it's using a pseudo-inverse, and if you perturbed your outcome variable y just a little bit, you'll find those coefficients will change drastically. So in that case, the pseudo-inverse is kind of useless, because if you change y a little bit, you're going to get a drastically different answer. And yet people just use the package and report the results. And very few people, I think, actually look at the condition of the matrix, right, to say how collinear are the variables, how collinear are the vectors, before they go about using, say, a least squares solution or any kind of inverse solution. Okay, so most inverse problems, or most least squares problems are going to be formulated like this: AX minus B, and we want to solve for X. And if you're familiar with the regression approach, it looks pretty similar to that. You're going to have y equals beta x plus epsilon, and you want to minimize the squared errors, the squared errors, and solve for beta. And so X is like solving for beta here, whichever you're more familiar with, what paradigm. Okay, so what some people have done is, well, very famous people that I'm standing on the shoulders of, have created a regularization problem to make this minimization problem more stable. So they'll add a lambda x, and that extra little constraint makes the problem more stable by pulling some of the lambda basically adds a constraint so that you're pulling some of the, say, weight of the problem away from ax minus b. So the larger lambda is, the more you're pulling away from the ax minus b. And the smaller lambda is 0, you're going back to the original solution. Okay, so but there's actually no reason, so here's my innovation. There's no reason why it should just be lambda x. Why should we pull the solution closer to 0? So I said, well, why don't we, I'm going to go back. I'm going to go backwards. I'm going to go forwards and then backwards. So I said, why not make it centered around x naught? I don't know what x naught is, but there's no reason why it needs to be x minus 0. I didn't write the 0. Okay, so what does this gain me? Well, what most problems do is they'll have an algorithm that sort of searches for the best lambda to solve this problem, and that's costly, takes time. And so rather than doing that, I'm going to have an iterative solution to this problem. What I'm going to do is I'm going to plug and replug x naught. Okay, so I'm taking x naught, I'm going to solve for it. Let me go back. I'm going to solve for it in this problem, and I'm just going to plug it back in. So x naught, so I'll have x1 as a function of x naught, x2 as a function of x1, x naught, right? All the way to the case iterate until I get to here. Okay, so that right there is almost what I need you to understand in a second. That's what I'm going to more or less program, but it's not the ultimate result. Okay, so let me just go back. So I said, persistent problem is how to choose this lambda, and that's why this approach, the iterative approach, doesn't depend so much on lambda as the regular regularization approaches does. So instead of computing one solution, I have a sequence of solutions, and that's what I'm going to program. And so what my solution does is I'm going to tell the computer to do however many iterations, it's k iterations. It could go from 20 iterations, 100 iterations. But the kth iteration is going to pass the true solution. So that's why I have this bird. It's basically going to reach the true solution, and then it's going to diverge again. So that's different from just, choosing the right lambda and then having the right solution to this minimization problem. Mine is going to do a number of iterations. It's going to pass the true solution, and then it's going to diverge again. So you need some sort of cost function to tell you if it's getting closer to the true solution or not. Okay, so the only last step for this is I have my xk, and then this is where Numpy is useful. I have to break this A matrix up using a singular value decomposition. So any matrix can be broken down into with a singular value decomposition. It just makes it easier to do, well, actually makes this math tractable, but if you want to read the paper and follow my derivations, I have it here, but what this does is it reduces it to just this formula, which is super easy to program. All I have to know is the sigmas, the lambdas, and then I have to choose a k, the number of iterations. So that's what's going into my package called inverse problem. It's on PyPy. It's also on my GitHub account. I'll give you the links at the end if you want to try inverting some ill-conditioned matrices. So that's what's getting programmed. I'll show it to you in a second. The other thing that I have not yet programmed is, remember I told you that cost function? So that cost function is going to be the difference between xk, the kth iterate, and the true x. also solve for that. And all I do is take xk minus x, do a bunch of math, and it comes out to this, also tractable. So this is your sort of your cost function that you can actually graph and see, is my solution getting close, and where is it diverging? And you can bound this. So just using a triangle equality, you can bound this. So the triangle equality, if you remember, like from Pythagoras' theorem, the triangle equality just says that the sum of the three matrices is less than the norm of each of them. And so we know we have an upper bound on xk minus x. The only issue with this that I still have, the only issue with this is, notice that in this expression there's e, that's the error. So that's the error term. That's the noise term. And so you have to, nobody knows what, we don't know, if you have a regression, you have some noise at the end of it. We don't know that noise, but you can have, so I don't know E, but I can have some sort of distribution on E or make some assumption about the distribution on E around the noise. That's the other thing you sort of have to decide on. Okay, so I haven't programmed this cost function in, well, I haven't made it in part of the package, but that's the next step. But I have plotted it. So this is an example. I'm sorry, the graph's so teeny. But this is a plot basically of xk against x for a particular inverse problem, and just plotting it with different iterations. So iterations going across, and then each line is a different lambda. So you have to choose lambda. But what's cool is that this solution is too sensitive to which lambda you choose as long as it's greater than 1. Because as you can see, if it's less than 1, it shoots off into the distance. So remember, this is the xk minus x. So the difference between the kth iterate and the true solution is shooting off into infinity. Whereas if it's less than 1, it's a convex. It's a convex function, so it's eventually going to hit the true x. Okay. So I just told you this, that you should choose a lambda equal to 1. And actually, after 20 iterations, most of my problems are good to go. You don't have to do that many more iterations. Okay, so I'm going to do an example. I had to put the Zen of Python into the package because I like it. So the package is called Inverse Problem. So I've imported it here. All right, so the first example, actually I'm going to start with the second example first. So if you're familiar with Hilbert matrices, Hilbert matrices are ill-conditioned matrices, hard to invert. And there's this nice package in SciPy that you can just use to create a Hilbert matrix. So I'm going to create a 3x3 Hilbert matrix here. And here I'm using the condition function in Numpy. So the condition of a matrix tells you basically how sensitive the matrix is going to be if you change a part of it. So I think like a condition value of 20 is reasonable for inverting the matrix, but anything greater than that, then you shouldn't be using those plug-in functions like pseudo inverse in Numpy. So just to give you an example, okay, so remember our problem is ax equals b, and I want to solve for x. And so what I'm going to do is I created a here. Okay, okay. So I created A here, and where did sorry, I didn't define B yet. Maybe I defined it up here. Oh yeah. So sorry, I defined B up here. So B is just a vector of ones. So we have A, X equals B. So A was my Hilbert matrix. We're solving for X. The solution is B. B is a vector of ones, okay? And so now I'm going to just perturb B a little bit. So the solution obviously should be close to, Sorry, I'm going to start with the other example. Okay, let's start with this example. So the first example is my A matrix here, and okay, so it's a matrix, first column of 1, 0, 0, and the second column is 0, 0, 0. And I'm going to perturb this matrix just a little bit by 10 to the 6, okay? So, sorry. So now I've just changed it just a tad. So now it's 1, 0, and then the second column, the second row vector now has just a little bit of a change. And now I want to just show you is, so the condition of the first A matrix is infinity, and the second one is also very high. And so now this is, my solution is B. And so if I use the plug-in inverse function from Numpy, this is a solution it gives me, which is pretty big. Like the second vector is huge. Now if I use my function and I choose a lambda, say 1, and I'm going to use 20 iterations, I'm plugging in the A matrix that I've changed just a little bit, and I've chose K and L. You can see I get pretty close to the right solution, so the right solution should be 1, 0. That's the pseudo-inverse solution for A not perturbed very much. But yet, when I change A just a little bit with this little added 0.000001, the solution changes drastically. It changes by 10 to the 6. So the point here is to show you that if I use the pseudo-inverse plugin to invert A delta with just that small change, the solution is drastically changed. Whereas if I use the iterative approach, with just a few iterations, lambda equal to 1, I get close to the original pseudo-inverse solution before I perturb the matrix a bit. Okay, so this is a similar problem with the Hilbert matrix. Now I can move on because I showed you that if you perturb A a little bit, then the solution for pseudo-inverse changes a ton, and if you use the iterative approach, it doesn't. You can perturb A. So the same thing, oh yeah, go ahead. Oh, well, I mean, I think in most large-scale, inverse problems, probably with regressions, it's very common. I don't know, like a percentage. I mean, I think more often than not, you're going to have some collinearity. The larger your data set gets, the more variables you have that are just like similar in nature. Yeah. So, I mean, it's actually, so like with images, it's going to be pretty common. With X-rays, you don't really need this for X-rays. They have, because the issue with X-rays is For images, for large images, this is useful, and for regression stuff, it's useful. I don't know. I don't know what to say, like how often it happens for any particular person. I don't know.
As a data scientist,
Yeah.
relatively often.
Okay. Okay, they're often. You need this. Let me.
The conviction you spoke about, you have like a validation set. It's like the machine learning, because you need like the real values to compare with.
Yeah, I mean, right now I'm just, so
Yeah,
I know the
you keep
solution.
some information that you know already what the result is. I mean, what, because you're looking for a result.
Yeah, I know. So that's why the cost function is, let me show you, I'll answer that in a second. So I couldn't do this here because it takes a little too long to run. But this is just an image, the original image. And all I did was, so that image is just it's a matrix A, and so with images it's a little easier, right? Because you can just tell that the image is getting clearer. With a regression, it's harder to know if at what iteration am I getting close to the solution, and that's why that cost function that I had, the xk minus x, would sort of, you could plot the results and see where it's getting nearer to x and then where it's diverging. And so once I program that in, then you'll have that. But with images, you can just see that you're doing better. So this is the original image, and then that's the image is the A matrix, and then I have a B, and I perturbed it a little bit, and I wanted to recover X. X is the image. A, you shoot rays through the image, just like the back. And then I perturb B a little bit, and I want to recover X. And so this is my recovery of X, the image, using different lambdas in K. So you could see that lambda equal to 1 is a good idea, and less than 1 is a bad idea. Functions that recover images, and it does a lot better. MATLAB did not do well. And yeah, Kachmar and Landweber or some other image recovery, but this does better. And so, yeah, and then you can plot, so this is just me plotting that cost function for different lambdas. So if you choose a lambda too small, that's the red one, then it just drops to 0 right away. So you don't pass by the true solution. And if you choose a lambda too big, it's going to take a long time to reach the real x. So lambda around 1, 1.2 is decent.
I think Bregman has a paper about this, like you should choose a lambda actually between 1 and 2.
Oh.
Projection onto convex theory by Euler and also from Russian mathematician Bregman has a paper about that. I think you should choose the lambda between 1 and 2 to do this kind of iteration.
Okay. Well, there it is. I'm glad I arrived at the same conclusion. So, so this is a good approach for very large ill-conditioned matrices. If you have small matrices, I don't know, like something like 100 rows or something like 100 by 100. No, that's big. 20 by 20, there's other approaches. So this is good for big matrices because because you're using this iteration, and the actual iteration doesn't take a lot of computing power. The thing that takes a lot of power is doing the SVD, but you only have to do it once. It's not like it has to do it at each iteration. It just breaks up the matrix, and then each iteration is just plug and replug. That's it. It's good for images because you can see what you're doing, but it'll be even better soon once I put the cost function in. What else? You have to know something. Well, So with that cost function, you'll have to know something about your noise. You'll have to make some sort of assumption about probably about the distribution of the noise. And if the data is really noisy, then this approach is worth. I mean, if the data is noisy, you can't recover anything. What this is good for is you have an ill-conditioned matrix, and you don't want the solution to be very sensitive to small changes in your observable data that you're collecting. So that would be your Y or your B. You don't want your inverse solution to change drastically. But if your beta is very noisy or your Y variable is very noisy, then even this can't help you. Then you're lost. So right now, I'll show you what's on GitHub. So it's very few lines of code, and all it is really, the magic is just right in this part. That's basically the XK part I was showing you, and then it relies on the SVD. Although I might have to do something, I might need to use something else, because right, the SVD is taking a long time with like very large matrices, which is why I couldn't show you the images example, because yeah, we would all be just sitting here. And that's it. Any questions? Are you excited? Are you gonna go use this on your X-rays?
So you're setting up the X0 on some kind of a path in each iteration, right? When you're iterating, you're updating the X0, X1.
I just X0.
Yeah,
It can just be a constant. I mean, it doesn't.
no, what you said that you're trying to predict that in addition to lambda.
No, X0 is just the initial value, and then I plug and replug, and so everything will be a function of X0. But X0 is just a value, and it could be any. You could start it anywhere. That's the nice thing. It's
So it could be like unstable with the initial
No,
value.
you cannot start from anywhere. That's the other thing in that paper. You should start from, I think 0 is the most stable point that you should start from. You cannot claim that you can start from anywhere and then this will converge.
you don't.
It will diverge if you start from some point, but most safe place that they mention is, I guess, like starting from 0 is a very safe place to start.
Yeah, but no, but so the original Tikhonov problem is not. Isn't doing this. It's not solving it iteratively.
No, this is about solving this iteratively, actually. Like with the projection of the coefficients. You have two projections there. You're projecting from one AX equal to B problem, and then like minimizing the length of the X, and then going on like alternatively iterating both of those. So if you start from a random point, it will not converge. We got like 2 minutes feedback about that when we were just like writing a paper about it. So I know.
Okay, I don't. It doesn't seem to. For me, it hasn't. I mean, what makes it diverge is the lambda that you choose, like I showed you. But I haven't seen anything. I haven't seen it diverge based on the X0 I've chosen or not chosen. I guess though, to be fair, in the solution, I'm sort of just doing away with X0 by setting it equal to 0 because it doesn't. Right, it doesn't appear in here. So.
Yeah, technically 0 is actually what they claim is a stable position to start.
But I should see what happens if I don't make that assumption and see if it diverges. I mean, it's not hard to change and plot. Okay.